Welcome back, physics students. Well, today we're going to be starting a new chapter. It's going to be chapter 19. We are skipping ahead. We're going to get to electricity. So chapter 19, we're going to learn about electric charge today. A little bit later on, we'll learn about the electric force. And towards the end of the chapter, we're going to be looking at combining electric forces. So let's first start by talking about electric charges, and let's start kind of at the beginning. It has been studied, that things can attract one another since the early, like it says there, 600 BC. Greeks have noticed that if you take animal fur and you rub it against an amber rod, it will attract lightweight objects. I'm going to kind of show you that. It kind of almost looks like a scene out of Harry Potter in a way, but I know you guys have seen this before. But if you take like this PCP or PVC plastic, which is right there, and you rub it against the glass, it's going to charge it up. So if I go like this, get it charged up, you'll see it's almost like I said, like a scene out of a Harry Potter movie there, where the stuff gets attracted to it. And there's even two, maybe I can get three. I guess two is enough, but actually it sticks on there pretty good. So yeah, we charged it up. So we've taken those two materials, we have charged it up. So one of them is gaining electrons, and one of them is going to be losing those electrons. So let's keep working here. I think you guys know this since your early stages of science. You guys know that like charges repel one another, and you guys know that opposite charges attract one another. This isn't new information. So like charges are going to repel, opposite charges are going to attract one another. All right, so there's two different types of charges. We have positive and negative. Ben Franklin proposed that glass would have the positive charge. He said that amber would have the negative charge, and that he knew that opposites would attract as well. So let's do a little chemistry lesson here. Let's talk about atoms in general. So atoms, we know can be electrically neutral. Atoms are going to have, if they have 5 protons, they're going to have 5 electrons. So they are going to be electrically neutral. There has 2 particles that can be found in the nucleus. We have the positively charged proton and the neutron, which would be electrically neutral. So here's a picture of an atom. So in the nucleus, you're going to have positively charged protons. You're going to have the little neutrons in there as well that are going to be neutral. You're going to have smaller electrons orbiting the nucleus. Now, electrons and protons are going to have the same charge, even though an electron is a lot smaller. So electrons are really, really small compared to a proton, but they have the same charge. They actually have it equal to 1.6 times 10 to the negative 16th coulombs, where C stands for the coulomb, which is going to be the SI unit of charge. So one electron has 1.6 times 10 to the negative 16 coulombs. So let's talk about the mass. We're still talking about an atom here. Electrons have a negative charge, but the mass of an electron is really small. The mass of an electron is 9.11 times 10 to the negative 31, compared to the mass of a proton, which is going to be 1.673 times 10 to the negative 27th. So as you can see, it's by like a fourfold there. You have negative 31 to negative 27. So a proton's like 4,000 times bigger than an electron. However, well, it says right there about 2,000 times larger than the mass of an electron. But it has the same electric charge, like that factor is still going to be the same. So we could go back. I guess what I'm saying here is, so if one electron has a charge of 1.6 times 10 to the negative 19th, one proton has a charge of 1.6 times 10 to the negative 19th. even though their masses are different. The neutron is going to be neutral, doesn't have a charge. The neutron is going to be slightly larger than the proton. So as you can see here, it's 1.675 times 10 to the negative 27. So it's just going to be a little bit bigger. But it doesn't do anything electrically to the atom. So like it says here, electrons have a charge of negative E, where protons are going to have a charge positive E, even though their masses are different. The one's 2,000 times bigger. The fact that electric charge comes in integer multiples of E is referred to as charge quantization. So it's like we're taking like 1E away, or 2E, or 3E. So it's going to be an integer multiple. All right, so a coulomb, let's define that. A coulomb is a large amount of charge. Since the charge on an electron has a magnitude of only 1.6 times 10 to the negative 19th, we can figure out how many electrons are going to be in 1 coulomb. Because if you take 1 coulomb and you divide it by the charge of an electron per electron, you're going to get 6.25 times 10 to the 18th electrons. It makes up 1 coulomb. That's a lot of electrons. That makes up 1 coulomb. So if that's how many electrons are in 1 coulomb, how many protons would be in 1 coulomb? Well, it should be the same, right? So a lightning bolt can deliver 20 to 30 coulombs of charge, which is a lot. A common unit, it would be the microcoulomb, which would just be 1 micro would be 10 to the negative 6 coulomb, which you guys have seen micro before. All right, so let's look at a problem on how much charge that we can have. So it says, find the amount of positive electric charge in 1 mole of helium atoms. So let's just say we have 1 mole of helium atoms, and we want to figure out the positive electron charge there. Well, what we need to do is we have to figure out how many total atoms we have. So that's what we do in step 1. In 1 mole, we learned in chemistry that there's 6.02 times 10 to the 23rd atoms per mole. So at this step, we've calculated how many atoms that we're going to have. But for each atom, there's going to be an X amount of positive charges in it. So if you look at the periodic table, helium has 2 protons. So you're going to have 2 protons per 1 atom. So if you take this, multiply here, this is how many protons you have. Okay? But if you remember right, so 1 electron has 1.6 times 10 to the negative 19th coulombs of charge. So 1 proton has 1.6 times 10 to the negative 19th coulombs. So that gives us an answer of 1.93 times 10 to the 5th coulombs, which is actually quite a bit. So like it says here, thus a mere 4 grams of helium contains almost 200,000 coulombs of positive charge. And obviously it's going to contain the same amount of charge as far as the negative as well. But yeah, so 1 mole is 4 grams. You're right, because you guys remember doing that in chemistry. It's because helium's going to have 4 grams there per mole. So, all right. So let's find the total charge of a system consisting of 3.9 times 10 to the 7th electrons. So here's where dimensional analysis comes into play. So we're starting with 3.9 times 10 to the 7th electrons. But here's the deal. For every 1 electron that we have, that's going to produce a charge of 1.6 times 10. I'm going to refer back, I can't remember the number, times 10 to the negative 19th, okay? So times 10 to the negative 19th charge. So we just take that value, multiply it times the charge per electron. So we're at 3.9 times 10 to the 7th times 1.6 times 10 to the negative 19th. And this will tell us the charge, which is going to be 6.2 times 10 to the negative 12th charge. Because that's what it's going to be. All right. Let's see here. We can try another one here where it says how much negative electric charge is contained in 2 moles of carbon. All right, so we're starting with 2 moles of carbon. We want to figure out the charge. This is going to be a 3-step problem. So 1, 2, 3. The first step is, well, in order to figure out the amount of charge, we have to figure out how many atoms we have. So we have to, step 1, take the mole and convert that to how many atoms. So this would be Avogadro's number, 6.02 times 10 to the 23rd atoms per mole. Okay. Okay, so now we have how many atoms, but in every atom, we're going to have an X amount of electrons. So if you look at the periodic table, there is 6 protons, so that must mean that there is 6 electrons per 1 atom. Okay, so at this step, now we know how many electrons are in the system, but we want to know the charge, so we have to use that new conversion. So for every 1 coulomb, or we're going to have the 1.6, let's see here on. So for every 1 coulomb of charge, it's going to be, here I got to look back, give me 1 second. So our unit is going to be 1.6 times 10 to the negative 19th. There it is. I don't know why I can't remember that one. So it's going to be 1.6 times 10 to the negative 19th coulomb per every 1 electron. So then this cancels, and we are left with the coulomb of charge, which is what we need. So then we're going to take 2 times 6.02 times 10 to the 23rd times 6 times 1.6 times 10 to the negative 19th, and I get a rather large number. Let's call this 2.0 so we can get 2 sig figs at least. We'll round it to 12. And 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So 1,200,000, that'd be coulombs of charge. All right. So as you guys can see that when we charge up something, we're going to be transferring the charge, and the charge is going to be in the form of electrons. So if we take these 2 items and rub them together, you'll see that this one gains the negatively charged, but when this one gains the negatively charged, it means this one's losing it, but when it loses it, it becomes positively charged. But electric charge is conserved. So if one of these gains 1, it means that this one will become positively charged. So you'll kind of see that this is going to be conserved. And another vocab word here is an atom that gains or loses electrons is going to be called an ion. You guys know that from chemistry. So like it says here, when 2 materials are rubbed together, the sign of the charged material depends on how well they want to hold on to those electrons. Some materials want to hold on to their electrons a lot tighter, so they'll become more negatively charged. Others could easily donate their electrons, so they become positively charged. So this way of charging up objects is known as triboelectric charging. So that's a vocab word for you guys. There's a table which is going to be useful for your guys' homework. So this would be like triboelectric charging. So like rabbit fur really doesn't care about its electrons. It can donate and get rid of them. So the rabbit fur will become positively charged. But on the flip side of the chart, like Teflon, really wants to hold on to its electrons. So when you charge it up, it's going to actually gain some electrons. So rabbit fur rubbed with Teflon makes a really good combination. Or glass rubbed with, let's just say, rubber makes a really good combination. If you try to take rabbit fur and human hair, they're going to be kind of fighting for those charges. They don't work necessarily as good with each other. I'm going to show you guys a cool demonstration here in a little bit where I'm going to take the rubber balloon and I'm going to use some of my human hair here, and I'll show you, and even the plastic bag, I'll show you guys what happens to that balloon when we run it next to the water. So here's kind of a fun question. If the mass of an amber rod, after charging it by rubbing it with fur, is that going to be greater than, less than, or the same before charging it? So amber rod, which would be down here, if you charge it up with rabbit fur, what do you think is going to happen to the mass of the amber rod? Well, to answer that question, you have to ask yourself, okay, the amber rod, according to the table, gains electrons. So if it's gaining an electron, is it going to be heavier, lighter? What do you guys think? And hopefully, you guys are saying it's going to be greater. And that's because it's going to be gaining a little bit of mass from the electrons. So the mass of the amber rod will be slightly greater after it has been charged up. Now the fur would be slightly less. Okay, we can charge up systems through colliding particles as well. A great example of this is if you've ever looked at a helicopter at night, the blades give off sparks. It's actually really cool. Planets do this as well, like Saturn. The rings of Saturn are moving really fast and it's colliding with the particles around it. And that's kind of what gives it its rings. It's basically the result of electric charges around it. So that's actually kind of a neat deal there. Okay, so now we're going to talk about polarization. The mechanism, well, polarization just means if you're making a molecule have a positive and a negative end, you're making it become polar. So water is a polar molecule, but we can cause it to undergo this polarization where all of the water molecules will kind of be forced to go the same way, like you kind of see here in this diagram. And a great example of this is with this balloon. I'll kind of show you this. I'm going to take this, I'm going to take this guy, and I'm going to grab the video so you can see it really good, because this demonstration is awesome. You can go home and you can really surprise your family, friends. So we'll use the sweatshirt here. We'll use some of the human hair. There we go. All right. So if I take this titration burette and I get a slow stream of water going, like that, then if I take the balloon and I bring it close to the water stream, can you guys see that it's slightly wanting to go towards the balloon? Pull it away, bring it back. That's because the water molecules are being all lined up and it's becoming polar. So that's just a fun thing you can do at home. You can surprise your family, friends. They'll be like, hey, that's actually pretty cool. All right. So I'm gonna put this back right here. So just a fun little experiment to try at home. All right. So like it says here, the water molecules are electrically neutral, but it's a polar molecule, and we can cause the water molecules to all face the same way, so it gets attracted to it. Okay. So let's talk about insulators and conductors real quick. Materials like amber, in which the charges are not free to move, are called insulators. So once it's charged, so like a glass rod here, if I only charge up this portion of the glass rod, it's going to be right here. Those charges aren't going to make its way up the glass rod and have this end be charged. So that's an example of an insulator. Now a conductor would be, once it's charged, its ions can be freed to move throughout the material. So if this was a metal rod and I charge it up, those charges would be free to be able to move around. Which this image does a really nice job of that. So this would be like an insulator right here. It's charged up here, here, and here, but it's not that the charges are going to be focused at one point. Where this would be like a metal globe, where we charge it up here, but they're free to move, right? They're free to move around. So conductors are free to move from one place to another, where the insulator is not. So the insulator, they just kind of stay where they got charged up. Okay, semiconductors will be a little bit of both properties, where they can be good conductors. Some can be good insulators, where they're able to free freely. So, all right, so that's 19.1. You guys will have an assignment on this on Schoology.